Today we're talking about atomic theory history. I call it AKA a bunch of dudes because it's really a bunch of male scientists and exactly how they contributed to our model of the atom. And you can see going across the bottom here, this is what matches the lesson in your unit packet. Model B is the very simplest, and we're going to go through all of these and end with Model C, our current model, the electron cloud model. First, let's go way back in time, 430 BC. There was a big debate. Democritus was the first to propose that everything in nature is really made of smaller things that he called atoms. And the story says that he was walking along the beach one day, and from far away he thought, wow, the beach really looks like it's made of one thing. But when you get up close, you realize that it's really a bunch of small things, aka grains of sand. Aristotle argued, all matter is made of one thing, it's continuous. So Democritus he ended up being correct, but neither philosopher had any experimental proof. But because of Aristotle's awesome reputation, more people believed him. And then there was technology. So along came improved scales or balances, and now they could actually accurately analyze chemical reactions. Because of this, John Dalton came out with his atomic theory in 1803. He said, matter cannot be created nor destroyed. He also said that atoms of different elements combine with other atoms in whole number ratios, meaning you've heard of H2O, but you've never heard of something like H3.070.1.29 because parts of atoms can't combine. Finally, he said matter is made of tiny, indivisible spherical particles called atoms. Indivisible meaning you can't divide them. Of course, we know now that number 3 turned out not to be quite so true. Think of splitting the atom in the atom bomb. So after John Dalton, they were really thinking of the atom as a small, tiny marble or a billiard ball. So it had no charge and it was very simple. But then about 100 years later, J.J. Thompson did some work with a cathode ray tube, which is pictured here below. And basically with the cathode ray tube, there is an electron beam, and you can put a sample into the cathode ray tube, and he noticed that every single element that was placed in it emitted a stream of particles, and he could see the beam deflecting. Therefore, every element contains these negatively charged electrons. The billiard ball model wasn't going to work anymore. So along came the plum pudding model. This was a dessert, apparently, pudding with raisins in it. And this is how they thought of the atom. They thought, okay, raisins are like these negative electrons, and the pudding is some positive stuff. Changed a short time later when Ernest Rutherford revealed his experiment results from the gold foil experiment. What he had was something that was emitting alpha particles. It was a rock that was radioactively decaying. And these alpha particles are really small. They're the size of a helium nucleus, so 2 protons and 2 neutrons. And so they have a positive charge. And he took not a piece of aluminum foil, but a piece of gold foil, and he pounded it, and so it was only an atom or 2 thick. Okay, so when he was shooting these particles through, most of the time they just went straight through and they were detected on this back wall. But every once in a while, one deflected, meaning it was like it hit something tiny. I think they said it was 1 out of every 8,000 times one of these particles was shot through. So this is how they concluded that atoms have a nucleus, and they also concluded that there's something positively charged in the nucleus, which they called protons. So in conclusion, to restate that, atoms have a dense, small nucleus that's positively charged. The nucleus makes up almost all of the atom's mass because electrons hardly contribute, and atoms are mostly empty space. So here we are, the Jimmy Neutron model. There's the nucleus in the center, and the electrons are circling around the nucleus. Along came Bohr. Bohr noticed that when you put certain elements in a flame, colors are emitted. And from this, he determined that electrons must not be at the same distance from the nucleus. They must orbit at different distances, just like planets orbiting the sun. So this is actually how the electrons would look, the planetary model. And he came up with this conclusion. We talk a little bit more about this later, but when electrons get excited, they jump up to an outer shell. And then when they come back down, they release that difference in energy as a photon of light. So because only certain colors were emitted, he concluded that, hey, they must be at these fixed distances, kind of like rungs of a ladder. Heisenberg also contributed to our modern model of the atom. He suggested that the location of an electron cannot be known precisely. You cannot know both the location and the speed of an electron. You can only talk about its probability. So he came up with something called electron clouds, and this is a probability cloud of where you're likely to find a single electron. And let's not forget about our last guy here, Sir James Chadwick. He discovered the neutral neutron in the nucleus, which was difficult to do because it doesn't have charge. It does have mass, and that was part of how he discovered it. So, here we are, the electron cloud model. So the nucleus is very, very small compared to the huge volume of the electron cloud. And there is a lot of empty space between the nucleus and the electrons, which are, again, in these clouds. We did an experiment in class where we took off the top of a Jiffy Pop and we put the hot plate on like a huge piece of paper, and the Jiffy Pop was just flying everywhere, and it eventually created this electron cloud sort of a thing because of the oil from the popcorn. How big is the nucleus? Just some fun analogies. If you blew up the nucleus to be the size of a tennis ball, you would have to walk 2 miles away from that tennis ball in order to exit the electron cloud. So obviously, the electron cloud is much, 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 much bigger than the nucleus. Baseball fans, if you blew up a carbon atom to be as big as a baseball stadium, the nucleus would only be the size of a pea. So next time in class, or maybe this day, depending on where this lecture falls, we're going to be building atoms out of Fruit Loops and mini chocolate chips. And so you're going to need to know some things about how to read these numbers on the periodic table. So at the top of the squares, that's the atomic number. It's the number of protons and the number of electrons if the atom is neutral, meaning there's no overall charge. Sometimes atoms can gain or lose electrons. The number at the bottom, which is usually a decimal, is the average atomic mass. It turns out that some atoms have a different number of neutrons, so not every single atom is identical. So some sodium atoms, for example, could have 12 neutrons and some could only have 11. The mass number is the rounded average atomic mass. It's a whole number, and it's equal to the number of protons plus the neutrons. So for example, the most popular form of sodium would have a mass of 23 with 11 protons. That means 23 minus 11, that means it must have 12 neutrons. Okay? The subatomic particles are protons, neutrons, electrons, and this table really does a great job of summing everything up. Protons are positive, they have a mass of 1 AMU, rather than saying, oh, they weigh 0.000000000001 grams, it's a lot easier to give it its own unit. Protons are located in the nucleus, and they determine the identity of every element. So if you know the number of protons, you know which element it is. Neutrons have no charge. They have the same mass as a proton. They're also in the nucleus. They're kind of like the glue that holds the nucleus together. Without having enough neutrons, the nucleus of an atom would fall apart. Electrons have a -1 charge. They're very small in mass compared to the proton and neutron, about 1/2000th. They're located outside the nucleus, and they're important because they determine the bonding of that atom, or how it reacts. So finally, if you're filling in your notes, notice going across, you're supposed to fill in all these blanks. And then same thing here, and you're only given one clue about the second one, that it has 5 electrons. So pause this video and try to fill this in, and then turn it on because I'm going to go over the answers next. Okay, so for aluminum, let's go across. Let's figure out where all these answers came from. The symbol, of course, is Al. The atomic number of protons and electrons are going to be the same. We're assuming it's a neutral atom. So that's from that top number. That's where we got that 13. The average atomic mass you just write down from the bottom. Now you'll notice that different periodic tables are more exact. Some have a rounded atomic mass. That's okay. But never round the average atomic mass yourself, because you'll do that when you write down the most common mass number. So 26.982 is 27 if you round it. So how many neutrons must the most common form have? Well, we've got to do 27 minus the number of protons. So that makes 14. Same thing here for boron. Boron's number 5, so it has 5 protons, 5 electrons. The average atomic mass we got from the bottom of the square. Round that and we get 11. 11 minus the 5 protons is 6.